dissertation of Radu Mariescu Istodor, Efficient Management and Search of GPS Routes. The opponent is Professor Walter Kropatsch from Technical University of Vienna. Having been appointed by the Faculty of Science, Custos of these proceedings, I now declare the examination open.
Honorable Custos, honorable opponent, dear listeners, I will begin my presentation by showing you a video that summarizes my work and some of its applications.
Nowadays, mobile devices have GPS, and many people record routes when hiking or doing other sports such as running and cycling. Route collections have grown so much that computers have trouble showing them to the user. That's why different applications show only a single route at a time. We found a way to show the entire collection by only keeping the points necessary to preserve the shape of the routes. When zooming out, we need less points. When zooming in, we need more points, but then we can cut out the ones outside the screen area. In this way, we can show many routes at a time, and even very large collections are now possible. To search through large collections, different applications use calendars or lists. But what if we don't remember the date of the route? Our solution is to let the user draw the route on the map. Then, the computer takes this shape and compares it with all the routes in the database using a fast, grid-based similarity measure. The best match is shown to the user. We have seen how to handle route collections, but are they really useful? Well, by finding the intersections and then grouping the in-between segments, we get a road network similar to the ones used by car navigation systems. The difference is that depending on how the routes were recorded, more personalized navigation systems can be generated. Our findings can help to improve taxi fleet management, path finding and orienteering, public transportation, ride-sharing, and parcel delivery, to name a few. So keep on tracking.
So first I will discuss about how routes can be visualized on the map and multiple routes can be displayed at the same time. Then I will speak about route similarity methods and how they can be applied for route search. And finally, I will show how you can infer the road network using only GPS routes from a database. We built a system capable of displaying multiple routes at the same time. My collection is with over 1,000 routes and over 1 million different points. This collection is quite big. In fact, if you were to download it as it is, it would be equivalent to about 25 very high resolution photos. If the user wants to see only a specific part of the screen, then we don't have to load the data outside of it. But still, this means quite a lot of information, depending on where the user is looking at. And it will take some time, depending on your internet speed, up to several minutes, with the conclusion being that the browser will fail to display this data. Our solution is to apply polygonal approximation to the routes, remove unnecessary points, but preserve their shape. This is done whenever the user is moving the screen. So if the user is panning or zooming into the map, a different approximation will be applied, and also more routes from the outside of the screen boundaries will be removed. In this way, we can drastically limit the number of the amount of data loaded into the system, and the browser will be able to display it appropriately. In fact, in the worst case, when zooming over Joensuu, where I have most of my data, I only load a fraction of the amount of information equal to less than half of a single photo. That means a couple of seconds. Let's see what other solutions exist and how they manage this problem. In this example, I present 6 routes using 3 different systems. First, sports tracker only shows the start location of the routes, and they are color-coded depending on the activity type. We can see many start points near my home because that's where I usually start tracking. One of them is at Science Park and the other one is close to the Linnunlahti beach area. Fränti shows a little more. We can click on these markers and show one route at a time. This is a skiing route on the lake. If we look in Mopsi, we get a bigger picture. First of all, the map shows a bit more data. It shows a wider surface area if we compare to the space shown by the other systems maps. And also, it gives all the information without the user having to click on anything. For instance, one of the routes even goes through 2 different other cities, even though the other systems just show Joensuu as the data. After we see a collection, we can analyze an individual route. This is done by all popular systems these days. But what they usually do is they do fixed length segmentation. In this example, Rantastic shows a segmentation every, the route is segmented every 10 kilometers. It is useful. It's showing us that the first 10 kilometers are fast, the next 10 kilometers are relatively slow, then a bit fast again. So this is an interesting route. It's not constant everywhere, and we learned something from it. But in Mopsi, we can do better. We use a different segmentation approach, which happens to identify correctly that the route contains 2 different segments of cycling, going to a location close to Joensuu Airport, and returning from that. And in between, there is a orienteering segment. So I went there to do this suunnistus. Let's move on to route similarity. It is quite common that we need to know if 2 routes are similar or not. Therefore, we invented our own method that does this inspired by something called the Jacquard similarity coefficient, which takes the routes, projects them onto a grid, and counts the number of cells that the routes have in common. It then divides this number to the total cells covered by the 2 routes, and we get a number. This number as such is not good enough, because even if 2 routes are close enough, it is possible that they end up in different grid cells. Therefore, we take into account also the neighboring cells of the routes and create a new similarity measure, which is slightly more complicated, but gives results that are much more intuitive to the user. This 62% is something that most people would argue it's a good number for this similarity value. And this is what other popular measures are giving. One example is inspired from string similarity. It's called the longest common subsequence because that's what it is. It finds the maximum length sequence of characters co-occurring in both strings. This can be applied directly to routes if we assume a distance threshold, in this case 50 meters, under which points are considered to be identical. The problem here is that the black route has many more points. It's recorded at a higher frequency than the blue one. And in this case, the numbers are skewed quite drastically. Another intuitive and quite different measure is called the Fréchet distance. This is basically the length of a leash that you need to walk a dog if you are walking on one route and the dog is traveling on the other. Similarly as before, we can declare a length for this leash, maybe 50 meters, which we consider here. But in our situation, you need a leash at least 500 meters to have this happening. So from that, we could infer a similarity value of 10%. We need 10 leashes to have this working. It is intuitive, but it's causing these problems, and routes are infamous, GPS routes are infamous for having noisy points. And one noisy point is enough to make this method unuseful. That's why another measure, dynamic time warping, averages, tries to pair the points from one route to the other ones, and averages this number to get a slightly higher similarity value. Another good thing about our measure is that it's fast. Its time complexity is linear, whereas the other ones is quadratic. And this is especially bad if the routes are long. It will take the computer a long time to find out this number. We can use the grid to find also other useful information. We develop other operations. For instance, these two routes are 50% similar, but if we look at only one route, it is 80% included in the other one. This is useful if you, for instance, think about the ride-sharing problem. Maybe a person can give you a right to work if this situation happens and it's identified by the system. We also compute something called the novelty. This segment is unique in the sense that the red route is the only one that travels in that section. And that's why we say that it's 15% novel. This is, can be useful, for example, in detecting taxi fraud. For instance, finding out if a taxi driver takes you on a longer way than usual to your destination, then that longer portion will appear as novel compared to the typical shortest path or alternative shortest path. Instead of speaking about route search, I think that I could show you how the search works. Let's take this example again, as before. A route that goes around the airport and the orienteering segment, and see if we can find it in Mopsi. This is my route collection from last week. I have just 2 routes here. It's not here. We can try loading more, but still that doesn't appear on the map. Not even loading my whole year's collection of 89 routes is enough. So I have to load the entire routes on the map, and now it becomes a bit tricky because we have a lot of overlapping data. So, okay, that was lucky. I could select it just by hovering in the correct location, but it's also possible that other routes appear when trying to select it in different parts. Alternatively, we can use a solution with route similarity. In this case, I just remembered the shape of the route, and I tried to draw it on the map. I remembered the squiggly part around the airport, and then basically I tried to tell the computer what I'm looking for. It does the search, it finds the result, and this time it even decided to analyze it for me. So it avoids the problem of searching through large collections, which typically in all the systems that we know at the moment is done by looking through large lists, like the one here, presenting all the data. Sometimes the list is better. For example, it can show the shape of the route also, but now this area is becoming much longer, displaying all the different ones. And this takes a lot of time compared to using tried to see how good these two search methods are. So we had a bunch of users trying the traditional search, where they find the route on the map, and the gesture search, where they simply draw the shape of the route. And we found out that using the gesture search, they get the results 41% faster. If we look at the individual user situation, we see that in all but one case, the gesture search was faster on average. And even the experienced users on the left, the ones that were very familiar with the traditional search, find the gesture search slightly faster. Let's move on to speak about road networks. Our solution to find the road network using just GPS routes is to first find the intersections. To do this, we look at many different locations, everywhere along the map, and ask the question, for instance, is here an intersection? We check if there is an intersection using a circular band like this, and taking only the route points inside this region. We then cluster the points, and we count the number of clusters. In this case, because we find only 2 clusters, we conclude that there is no intersection at the location. But if we try this search somewhere else, we might have a different story. Anything more than 2 clusters usually means that an intersection is at that location. So repeating this process, we eventually find the intersections, and then we can move on to the next step, which is building the roads in between. And to do that, we use averaging method and find the best representative considering the routes that are passing between the two, every pair of intersections. We decided to evaluate our approach on 2 different datasets. One in Chicago, recorded by University Shuttles over there, and the other one in Joensuu, which is part of the Mopsi dataset. We compared our method with 3 other very popular alternatives. First, a visual approach, which uses image processing techniques to find the network. Secondly, a clustering method. This one disperses seed points at locations throughout the space covered by the routes, and then connects them to form the network. And finally, trace merging approach, which uses physical forces on the routes and attracts them into what will become the representative segments. Our conclusions are that visual methods are very precise. When they find the segments, they will find a very accurate representation of that segment. But they miss some data when too few routes are in the region. Therefore, we compute an F-score for this measure around 45%. The other 2 methods we compared with have the opposite problem. They find too many segments instead of only one single representative. And this causes for high recall, even though the precision is quite low. So the F-score is the lowest for these 2 measures. In our situation, we have a balance. We find good accuracy segments, and we don't have so many false positives. F-score is highest for our method. Yeah. In conclusion, I showed how large collections can be visualized on the map, and that it is possible to show them, not just starting points or one route at a time. We saw that route similarity is useful when searching for routes, but also enables the user to find them using this gesture type of input. And finally, that road networks can be extracted from the root page. I ask you, Honorable Professor, as appointed opponent, to make those remarks which you think that my thesis will require.
Thank you very much for this presentation. In this first statement, I'm asked to comment on the scientific meaning of the dissertation subject. And since this is a public defense, I think we should involve the public. And that's why I would ask the audience, who is aware whether he has a GPS in his surroundings or not? Please raise your hands. Okay. That's about 50%. And you are very special people working at the university. Now take the population of Yonzu. That's about 75,000. So if we can't compute now, we have 75,000 people. Let's say a little bit less than 50% is 30,000 people who are collecting roots, who have the ability to collect roots, either by running, as you do, or by driving a car, riding a bicycle. We saw many bicycles in front of the university. Now, guess how many roots can be generated by such amount of people, and this Joensuu is only a small village. Imagine you do the same thing in Helsinki, or Chicago, or Washington DC, or bigger cities, and each route contains many points. 10,000 have some of your routes. That creates a huge problem for storage and recovery. And I think your work contributes a lot in order to make such collections usable. But otherwise, if you have to wait an hour until all the routes are downloaded from the internet, then nobody would care. So you need fast reaction from the system in order to cope with the huge amounts of data that are available to make use of them. And you have shown in the last application how to use your tools to generate a road network. So much about the importance that I would give to the work you have done. And since it should be short, I finish this first statement here. Now, we can sit down, I think. Of course, there were some questions open. Shall I use the microphone, or does everybody hear me? Okay? Who does not hear me, raise your hands. Okay. My first question, I'm from computer science, and I studied also mathematics. So my first question is, what is the precise definition of a GPS route? Because you were talking about GPS routes, but you never considered now that you have the GPS sensors. They have certain properties, certain problems in generating proper coordinates for the location. Okay? And this influences the further processing. You showed us some improvement, but I would like to stress, now what is a GPS route? Can you give a definition?
I think we can define the GPS route as a sequence of points.
In which dimension?
They are two-dimensional points on the surface of a sphere.
Yes.
So the coordinates are degrees, and the radius of the sphere is given as a radius of the Earth, at least it's estimated. The points are recorded by a GPS receiver, hence GPS route. The sequence of points is ordered And usually the points along with the location information have also timestamp information.
Okay.
In that case, it is useful because if you just have the ordering and maybe a delta between the point times, if the signal is lost or weakened at some point, we might have a longer gap between.
I don't know if everybody is familiar with the principle of GPS. How can a point be lost? Can you shortly explain this?
Well, for instance, if you are traveling in a car
Yes.
and recording points every 2 seconds or every 1 second, and at some point you enter a tunnel, then the path to the satellites which are used to obtain the location is lost. So temporarily, until you exit the tunnel, there is no location information available. In that case, having every point associated with timestamp is useful because we know when the user was at a specific location.
Okay. Now you, this is very valid if you have a relatively flat landscape. Now I'm from Austria, and Austria is not such a flat country as Finland is. We have high mountains, and Finland has it. I think Finland has a bit about 1,000 meters. Is somehow the highest mountain, and it's not very has not very steep flanks. Okay, so in Austria and also in other countries, I have one example. I think this is probably interesting to know. I was last year on a workshop in Marseille, and Marseille is on the coast, and on the coast it has a very steep slope. Okay, we rented a car at the airport to go to the conference site, and my colleague had a Google navigation system, and she told me how to go through the unknown city. It worked perfectly, and then Marseille has many tunnels, and the tunnels, okay, you said already there are occlusions for the GPS sensor, but not only this, it somehow our navigation system tried to interpolate where we are on the map. And after I entered the tunnel, the navigation system that my colleague communicated to me, listen, Walter, in 200 meters you should turn left. Well, it was in a dark tunnel. I used my natural intelligence not to do what the navigation system told me to do, knowing that there are probably some problem, because it was not so stupid, because it saw only the ground projection on the map, and there were roads above the tunnel, okay, which would be a good continuation. So that's why the system thought, okay, you are very close to the intersection, so you should turn left, which of course at my altitude would be very difficult and would cause an accident. Okay, now my question to you is, how could you include in your GPS route the altitude? That's why I also asked before about the dimension of the data. To make it usable for countries like Switzerland, Austria, where you have many different altitudes, so length, okay, plays another role. Like if you talked about running, okay. Now if you run up a mountain, okay, you're probably much slower than if you run down a mountain. Okay, that somehow explains also why you get different speeds from a Mopsi if you record it, if you climb a mountain. But also there, probably the altitude, to include the altitude to this two-dimensional coordinates may be useful.
GPS system is capable of obtaining also the altitude, but the accuracy is so low
Yes.
that it is not computing it reliable.
Mhm.
That's why there have been other approaches to this. Typically, the most commonly used approach is a surface, for instance, Google,
Mhm.
is mapping the surface of the planet and computing the altitude using a barometer or some other way to then use together with the route, which is a separate data object, and assume that the height, the altitude, is on top of the surface where the height information is available. But in this particular situation, I think that such a solution will not work, because it is possible that the altitude information comes from the roads above your tunnel.
Yeah.
A possible solution to this would be to predict where the user is driving,
Yeah.
that he will pass through a tunnel, and not to use the height information in that scenario. I don't think that this is done by current navigation systems. If they find that you are off the intended track, that you are not turning left in that scenario, they will compute a new path for you.
Okay.
I don't know if this fully answered your question. But,
Well, it goes in the right direction. I have some additional ideas about this, because I know that in many countries you have very good height information on maps. So there are geocoded altitude maps, height maps, which you could use because you have a precise measurement where you are, okay, which you could enhance by the altitude that is given by other maps. Okay? So, and this is also not a very lengthy process, because you can directly access it. Mostly there are grid-based terrain models where you can, I think in Austria it's by 50 meters. They have the same accuracy that you have in this GPS system.
I understand. Such systems can be used, except in those overlapping road situation, high roads, or other situations. For instance, if we are speaking about a bird with a GPS tracker, or a plane. At the same time, a ship, because then the altitude that you would get in these devices is the bottom of the sea.
Yeah.
The water is simply a heavier air, if you may.
Okay.
And then if you're on the boat, or maybe walking on a lake in Finland, this is quite common.
You mean to that?
Yes, then you will get wrong information.
Okay.
So
what would be a mathematical requirement for the surface which you are dealing with?
I think a barometer in your mobile phone would be a first step. Because then you can put, yes.
But even the terrain models can cope only with a function of height. They cannot represent a tunnel system. Because at the tunnel system, you have multiple values of height. One of the tunnel, and one at least of the top of the surface on the beach. And there are caves, for example, which are very popular, where you have even multiple altitudes at the same point. If you would drill a hole, you intersect many tunnels of the cave. Okay? For this type of surfaces, I think you would need other tools to cope with these situations.
At least one way would be to have a three-dimensional road network of this region.
Well, yes, but how do you represent it? Because it cannot be represented as a function of two-dimensional surface.
I think a different approach would be needed.
And higher complexity.
Yes.
Because you need to move on the surface may have holes.
I see. Yes.
Okay? That's also for ships.
Mm-hmm.
If they travel on the surface of a lake, but Finland has many lakes, but every lake has many islands. So an island for a ship is a hole, because it cannot go across the island. So it has to go besides. And this involves quite complex strategies to optimize path lengths, for example. Okay. So we know that these surfaces on which you place your roots, the root essentially is a part of the surface. It's a linear, it's a one-dimensional manifold which is embedded in the two-dimensional manifold of the surface. And it's sampled. Okay? Yes. And of course, I think to give it again a larger scope, they are currently planning higher precision positioning systems, because the current GPS is quite old already. It was developed for military applications, and it's probably better accuracy than we get in commercial use. They don't provide this accuracy that military use from the same GPS system. Okay, but future, I think Europe is planning an alternative to the GPS, because the GPS is essentially trademarked by the United States. Okay, and Europe doesn't want to be left without coordinates. Once the US decides, okay, we shut off our GPS system, so the others cannot navigate anymore.
If I remember correctly, there are some alternatives, I believe, one in Russia and one in China that offer the same same possibilities.
But with different parameters, different accuracies and so on. But Europe is also planning on. My question now to you would be, how flexible are the tools that you have developed in order to adapt to a new GPS system? That's coming back to the definition of GPS route. Because if you exchange the sensor, of course, you may need to adapt your processing strategies to the new parameter, higher accuracy, probably higher dimensional representation, giving better precision in altitude.
At the moment, we disregard altitude from our methods. Okay, so consider that everything is happening at sea level or at the same altitude information. Okay. One of our parameters is when using this grid to represent the routes is the cell size, and it has been chosen in Mopsi and simply through experimentation to be 25 meters. This length was chosen to be 25 meters because one of the reasons is the GPS error at the moment. So I believe that if a new system with a better accuracy would arise, then our method would need to update the cell size parameter to something smaller. Okay. I don't know if this if the new size should be proportional to the GPS, the new GPS error, to the error change, or but it should at least correlate with it in some way. Other than that, I think that it should cope with a new system. Perhaps maybe this interpolation stage that we if it would be possible to record at a higher sampling, to have higher sampling rate, then we might not require interpolation or less of it.
Very good. So we know what a GPS route is. And you gave it the next keyword that was a grid. Now, if you type in grid in Wikipedia, you get at least 8 different definitions of what a grid is. Can you tell us what is a grid you are talking about?
I think that an informal definition would be what you see when you open a math notebook. The style of the page, the small squares in which you can write the numbers, the format, everything nicely. To put it more formally, it would be a division of the space into equal-sized cells distributed in horizontal or vertical orthogonally in the space.
It's a square.
Yes. It's a square.
So how important is it that you use a square grid?
I think the shape is not that important, but there are only a few choices that we can have to tile a surface, a flat surface. I think that they are the square, triangle, and hexagon shape. The benefit of using a square grid is that the number of the neighbors of the grid and the relationship with them is more straightforward. You have neighbors on the top bottom. We can refer to them as north, south, east, and west, and also in the diagonals. Whereas the relationship in other types of grids, like the triangular or the hexagonal, become slightly more complicated. The number of neighbors might be.
Well, it's less with the triangle.
The triangle is less, but it might also cause a rotation artifact.
Okay. Isn't it that the advantage, big advantage of a square grid is that you can address every cell at 2 coordinates?
Yes, that is.
The direct access to a cell in a square grid has big computational advantages because you can directly address a cell. But just in principle, you can see it as integer coordinates. You first transform it, the scaling, to the size of the grid, and then you cut off the decimal numbers behind the comma.
Yes. Yes.
And then you can immediately address every cell. But in principle, the question is how important is the direct addressing for your algorithms?
The only place where we use it is really in this interpolation step and also in the dilation step.
Yes.
If these 2 steps would be replaced with something else or removed entirely, I think we don't need direct addressing of the cells.
In that case, wouldn't an arbitrary partitioning of the surface also be sufficient? Just mixing triangles, quadrilaterals, hexagons, pentagons as the data are needing. Because you have, if you are recording routes for running, well, what's the purpose of having a very fine resolution square grid over a lake? if you are not talking about winter running. Okay, you don't need these cells.
We use the cells as a unit measure when talking about root similarity, for example. We are counting the similarity as the number of cells in common shared by the roots. And this number of cells translates into the, maybe we can consider it the common distance traveled, okay, by the roots. So I think that the shape might not be a constraint, but maybe the surface area of these shapes should be uniform, okay? Because then we can consider, I'm not sure if this is sufficient, but at least the first requirement should be this, okay? Because then
You replace the continuous measurement by a discrete measurement, which counts the number of cells that the root visits on its path. Okay? What is the accuracy? Now, if you go in continuous coordinates, you have a continuous curve. You can have arc length geodesic distance between the end point and the starting point. That's a precise measurement of the length of a road, of a route. Now you sample it, you make a first approximation error. Because you get only a subset of points, of the infinitely many points, and calculate the Euclidean distance between successive points, and you sum up these distances as an approximation for this curve. And then at the next approximation, you count simply the cells that are touched by the root.
in practice, I think that this approximation is not such an extreme decision to have. I think that what you missed is that the root is not simply the GPS root is not simply a sampling of the continuous curve, but it's also an approximation of the true location in its first form. And that we are already dealing with approximated data.
Yeah.
And we don't expect to have precise results because of that, because of this implied error in the way the systems are able to.
Yeah.
Therefore, having slightly less accurate data is not a big damage from the application point of view. And through experimentation, we found that choosing a suitable cell size, this 25 meters, which I mentioned before, is applicable for the type of data we and also other data sets that we have used in our experiments for us to cope with this data. But it is true that we are working at a even less accurate level than we could.
Okay. So you said you have different sources of errors. And of course, an immediate question that comes with it, do these accumulate? Because you can have one type of error, yes, and then you add up, that's the inaccuracy of a point. Then you have the inaccuracy of your sampling, which has a different source, okay? So essentially, the maximum error that you can have is the sum of all the errors.
Yes.
And how large is it for the system that you're using?
think it's highly dependent on the region where we are looking at. In Joensuu, I would say cumulated errors, maybe normalizing them by the number of points. I think it's fair, because longer route will have more error and shorter route will have length. So if we consider the average error per point instead, it would be roughly 2 to 5 meters.
So you're using sort of a regression method for, if you do interpolation, it's essentially a regression. But it's known that for regression, an outlier may have really strong effects on the outcome. Mm-hmm. Okay? So now, if you think of reflections, for example, in images, they may completely destroy, even if you have many correct points, a single point which doesn't fit your model would degenerate all the parameters of the model. Mm-hmm. And the question is, can this happen with GPS data?
Yes, yes, it can. It happens quite commonly that one or few other points are translated from the original location by a given factor. In meters, it's possible even up to 100 meters away from its original source. And this is a problem. We handle it in some situations where we need more accurate interpretation of the results. For example, in the route analysis, where we are computing the speed of the segments, we do a filtering stage at the beginning, where we identify these isolated points and remove them from being part of the route.
Okay.
We identify them by looking for abnormally large speed signatures. Okay. Because if your point is at the location A and then moves due to error 100 meters away after 1 second, it is reasonably okay to assume that we can consider it an outlier. Okay, take it out.
So this makes an implicit assumption that you have a certain range of speeds that you are following.
Yes, and we found a problem in the system when I was tracking inside an airplane.
Yes.
And
because it's not higher speeds.
Because it was in a much higher speed. And it was considering that everything there is an outlier.
Okay.
We didn't fix the problem.
Okay.
But I think that it is possible if we simply look at the whole route and see that a clear pattern exists. It's not just, the location is not just jumping randomly, but following some path. And a better system can be implemented. But at the moment, car, cycling, training speeds are working at no point.
There are now newer methods since 10, 15 years in the area of robust regression, where you integrate in the optimization term the number of outliers that you don't want to consider. So you have a model, like in normal regression, okay, which allows you to find out what are the best parameters for the model. But you have a second term, an additive term in general, okay, where you say, okay, but 5 points I don't want to consider. Okay, leave out 5 points, the worst 5 points, as you said before, and there is a whole theory beyond this. Of course, one has to consider the complexity of those algorithms, because in general, they are pretty slow. Okay, so but this would be a potential extension for coping with outliers. Because otherwise you just, now you have one outlier of, let's say, 1,000 points, okay? So you consider this. But you may have, like you said, with the airplane, you have 100% outliers where you cannot generate any result if you have a fixed parameter for what is an outlier and what is not an outlier. That would be probably potential extension.
Yes.
Okay. Good. Let me come to another issue that I noted. It's we defined the GPS route, defined now the grid, which in principle could be also something else. Okay, and any partition of a plane probably could be used for. And then we use several times the term cell. Okay? Now, what is the relation between the grid and the cell?
The grid is made of cells. And
Actually, I would disagree.
you would.
Yes.
Okay.
Because the grid essentially is a collection of points. Because we said we address them by integer coordinates. So these are points.
I would say that the grid is made of cells, and that each cell is represented by is indexed by a point. So the indexing of the cells is what we were referring to beforehand, that we can use two digits, two numbers to represent.
Yes.
But the cell itself has a shape. You mentioned it can be
Yes.
arbitrary. In my case, they are square.
Yeah.
So we were speaking about the indexing of the cells and not the actual cells being these numbers.
Okay. What would you think of the following definition? If you take the points of the grid, maybe a triangular grid, a square grid, or an irregular grid, like in computer graphics, they use triangular grids which are nowhere regular because they are measured points essentially. Okay? Because then they can display the surface normal for a triangle. That's the main purpose. Okay? Now, the points of the triangles are the corners. And the triangle itself is the dual of the graph if you connect the corners with each other, which generates a dual graph of the grid points. So you have the grid points, which determine the vertices of a graph. Now you have the neighborhoods of the grid points. You mentioned it also before, okay, which determines the edges of the graph. Okay? And since you are talking about a two-dimensional manifold, the graph is planar. Now, if you have a planar graph, you can consider the dual graph, which consists of the faces that are enclosed by the edges of the grid graph. And everything, I think, would work.
So you are speaking about representing the grid and the cells inside the grid as a graph specifying their connectivity.
Yes. And you have two different types of connectivity. There are the neighborhood of the grid points, okay, and there is the neighborhood of the cells, which is not the same.
Yes. Yes. Okay. And is the neighborhood of the cells implied somehow from the neighborhood of the...
There's a bijectivity
between
between the edges of the grid graph and the edges of the dual graph.
So one of them can be found out using
Yes.
the other. And it has to do with this planar graph property.
Yes.
Okay.
And it is also related that what we discussed just before, that you have a two-dimensional manifold, like the surface of the Earth, which is a two-dimensional manifold without holes, okay, without tunnels and so on. And this would be a possible rigorous definition of a cell. And then I think everything in your algorithm would work with this definition.
It would. But it's not so simple anymore. I think that key to have a solution to be used and to be used by others, implemented by other people, is its simplicity. If you are speaking about real applications, maybe as we discussed before about this routing in the watches these days, I think that discussing about these two-dimensional manifolds and about planar graphs and these kind of concepts, that people that aim to implement such solutions will discourage them from using them. And one goal in this work was to explain it more to the masses, to have it more, to have a simpler solution that is easier to be implemented and used.
Well, the user doesn't care really what data structure you're using to provide the results.
It's not for the user, it's for the implementer of the solution.
Okay. Well, but I see, at least in the field of pattern recognition, if you look at the SSPR conferences, there is an increasing number of papers dealing with graphs, and much less than with conventional filtering square grids. Because the main advantage is that you can cope with topology. Okay? Where square grids essentially do not cope with topology. You everywhere have the same topology.
Yes.
Which has advantages but also drawbacks.
Yes. I understand the point, and I see that you're implying that this all these methods can work in this new way of representing the data. It's a more general analysis that is good for science and might enable more applications than what we have covered so far.
Yeah.
Just believe that these current solutions should be used somewhere, and keeping them in a simpler, more specific form might make it more possible for them to be found by others.
But I agree with your comment that implementing a graph structure is much more difficult than using a grid. This for sure.
Especially a square.
Okay. Yes. Okay. In addition to this, you are talking to about a landscape and about persons who run in this landscape. And the question is, now, you don't run across the jungle in general. You don't run across a lake if it is not frozen. Okay? So what is the relation between the geometrical issues that you are properly dealing with it and the semantics of the landscape of the map? If you talk about roads, road networks, usually cars move along roads. And if you know where the road is, okay, there may be other similarity measurements than just geometrically closeness. I have one example which should illustrate this. If you have a 4-lane divided highway, okay, 2 lanes go in one direction, the other two lanes go in the opposite direction. Okay? Now, you compare the route of a ghost driver, which goes in the wrong direction, on the bypass on the wrong lane. And you compare it to the route, which is on the opposite of the division. This is very similar to the two cars that go in the same direction. Although one situation is much more dangerous than the other. So this just to illustrate that semantics may also be used, for example, to identify errors. Because if at one point, if you cycle along the lake, okay, and suddenly one point is on the water surface, you immediately can guess, well, this is probably an error, an outlier. So you don't need to measure how far it is away from the coastline, because you know for sure if it is in the water, then it's very unlikely that you're cycling across the water.
Semantics can definitely be used to enhance the methods.
Yeah.
It also poses the problem of having this information available, and it's widely available when working with Mars, for example, and road network is common in most countries and all over the world. But that makes the problem of dealing with what are the possible types of terrain that we are working with, and the constant change of this terrain, and enabling the methods to work with other types of terrain. For example, if we want to apply the methods in the application of wildlife tracking,
yes,
they will not follow our network. And in that case, it's perhaps better not to use semantics at all than to use limited or maybe even wrong ones because of constant changing of terrain such as forest fires or river spreading of directions. So if semantics are available, they could be used complementary, I think.
Okay, to help it. Yeah.
Not as a prerequisite for the method to work.
Mm-hmm.
So that's my
Okay. Very good. You mentioned a few further applications, like birds tracking. What
you
other? Yes, but I think you have designed a system now. Why not use the same system for other types of applications? I think that's should be a selling strategy.
We will. We are.
And the question is, if you have a new, you mentioned it partly already, that you don't want to use semantics because there may be a change in semantics with different applications. That was the argument. And I agree with the argument. But the question is, how could you adapt? Because you will not mix the data from bird migration with the running routes of Pasi.
I think that it is a matter of pre-processing or online prediction. We want to find out who and or what is carrying the receiver, is doing the tracking first. And this could be done by fitting, for example, the root or the current root points to the multiple different semantics databases.
Yeah.
And then see which one makes sense.
Yeah.
I see many different ways this could be implemented, but it is not. It is only necessary if you want to improve, to get more accurate readings, not for the methods to work.
Yeah.
So I don't see. I still don't see why you aim so much at using this type of additional information.
Because it may be useful to make obvious decisions which are very hard to decide from a geometric point of view. That was the main argument. Okay? So if you search for outliers, semantics can help a lot. Because the driver on the wrong side of the division, okay, goes in the wrong direction. So if you know this is a one-way and the direction of movement is the opposite direction, this is wrong. So the semantics can help a lot in crippling. I think humans use human intelligence to solve critical situations in this way. Okay? And the question essentially that I was asking, how can you connect what you do on the level of geometry with what people in artificial intelligence are currently doing? To make a bridge between the different fields and to find more efficient solutions than to find a very complicated metric to identify an outlier. Because the outlier has to do with its interpretation.
I think that that was my answer before. To find out first what is essentially doing the tracking, and then applying it, applying the additional information. But I don't see reason to apply this unless it is really a need. Functions. Okay, you mentioned before some examples where this is a mandatory aspect, and I agree with that. I think that in most situations, however, semantics is an additional constraint when implementing these methods. If we speak about the simplicity and the hopes of having them applied somewhere else.
Well, the simplest implementation of semantics would be that you take your cells and you have semantic attributes
For each of them.
associated with every cell.
Yes.
Then you immediately have the possibility to compare whether you are on water or not. So this would be a very easy way. Actually, these are semantic maps, essentially. We have the type of coverage of the Earth represented as a label, as a symbolic label.
I agree that this is simple to do, but the fact that the world is changing brings the problem of updating this information. And updating this information needs extensive effort. For example, maybe by using aerial imaging techniques or actually visiting the terrain and marking it. It can be done partially automatic, but it's not just idea of using it, but also using it reliably and not having it cause more harm.
Well, there are departments at different universities which deal with this aspect of keeping up-to-date maps of all areas in a country. Geography departments and geographic information systems, they all provide such semantic information. And the question would be, how do you couple it so to make not an additional obstacle for generating efficient answers? Because if it would slow down the answer, then it would not be useful anymore. Okay, I completely agree. But computers get faster.
Yes.
Okay, and there are nowadays efficient methods to address also this type of information. But I think the question was again going in the direction of what in the future could be done based on the research, and it's of course related to the contributions that you make to the scientific knowledge. Okay, because there will be other generations of students who will, because the whole thing is not finished, I guess. Okay, so there will be lots of open questions that are related to this. Okay, good. I think time is progressing. I should come probably to my last question. Okay. I think you don't guess what it will be. Let me ask first the audience. How many of you are PhD students? Raise up your hand. Okay. Now, comes my question to you. So you spent several years on doing your PhD. Your Romanian colleague that was with me some years ago, he called me always Dr. Father, and he called himself Dr. Baby. Okay. Now, what would be your experience? What you want to communicate to your colleagues, which are in the situations you were several years ago in doing your PhD? What is your experience, what to do and what not to do?
Okay. Well, I didn't expect.
This is not an expect.
I didn't expect to get this skeptical question, but I liked being doing my PhD, and considering that maybe other people would like similar things as I do, I would recommend to try to listen to the other groups, the other colleagues, and when they say that they are facing some problem, don't just forget about it and worry about your progress. I would say, see what that problem is, see if you know an idea how to solve it, and do that. And don't limit yourself to doing your PhD. Try helping others get their PhDs also, and you will see that the help you give comes also back to you in other forms. And the idea of research is to find new things. It's to find what works, what doesn't work, why it works. It doesn't matter about the topic very much. And by helping others that are stuck at a specific problem, you are advancing research in general. So I would say don't limit yourself to your own topic, and try to see what else is out there. Would be my suggestion.
Have you ever been in a sort of dead end
You expected to go in a certain direction, and then suddenly you see the expectations are not satisfied. Okay? I think that's a typical situation in research. What to do? And partly you answered it already, but I think you should also find a solution for yourself.
I have an index for them. I have multiple dead ends. Don't get stuck on the dead end. If it is looking like hopeless now, it might not be hopeless after 1 year. But in that year, you can do something else. You should do something else. Try having multiple directions, and keep track of your dead ends, because sometimes it's very surprising how the solution comes from somewhere else, but you won't find it unless you look somewhere else. So it is this type of always keep track of what you do, and be meticulous. Have a calendar, have a list of things, history, and look at it from time to time. So I find it very helpful. I don't know what else to say.
No, that's. Let me add one thing, which I consider, and I saw a mistake in many diploma theses and PhD theses, document also the wrong results, the unexpected results. Because at the end, when you write down, you need to argue why you did not follow the dead end to avoid that others ran into the same dead end. That's part of the scientific knowledge.
I think you are right, and I agree with that. People should publish negative results. If they have a result that is intuitive, but it does not work, then this is surprising. And if it's published, other researchers know not to waste time following this same problem. But unfortunately, these days it is better now. But many journals would don't even accept this kind of negative results. So I don't do it consciously, but I think that I keep many of the results cooking, many of the dead ends to stay there and find a solution in the future, hoping for finally a good result to come. I do often in different papers mention what hasn't worked.
Yes.
But I'm hoping for it to also have what did work, because then it tells a larger story. And it ends up in better journal, maybe with a better chance of being read by more people. So I think there is a balance here between these two.
So that ends my questions. Are there, I think you asked for general questions, or are there final statements? Okay, my final statement, so we stand up. So, we have discussed a lot about your work, and I think the overall topic and the relevance to computer science you have nicely shown. So also I hope that the audience agrees that you have demonstrated that the novelty of your approach, and also the experts that reviewed your thesis have shown this. And in summary, I got the impression that your research and what you have documented and demonstrated today qualifies you to act as a doctor in the future, which means a lot of work, new work for you. Thank you for our audience.
Anyone in this auditorium who has anything to object against my thesis, please ask the Custos for permission to take the floor.
I now declare the examination concluded.
I would like to invite everybody here to have coffee and cake in Custos restaurant.